What does nothingness contain on Earth? A cubic meter of air seems like almost nothing. It is only equivalent to about 1,000 human breaths. And yet, compared to the average of the universe, it is one of the densest regions that has ever existed. Within that tiny volume, the largest creatures that can swim through it are bacteria, drifting along wind currents, wandering in search of a place to settle. Some of them spend their entire lives suspended in the air. Accompanying the bacteria are countless microscopic fragments, dead skin, droplets of saliva, mucus exhaled and dispersed from living beings across the planet. That is all the complex molecular structures that human senses simplify into smell. And then there is the air itself. Nitrogen and oxygen in diatomic form, carbon dioxide, water vapor, along with a host of rarer molecules such as methane or ozone. But that still is not everything. Almost every second, a cosmic ray pierces through that tiny volume of space. It is born from immense energy processes in some distant part of the universe, a star exploding, or a black hole collapsing. This particle has wandered unimpeded for billions of years, only to end its journey when it collides with an unlucky air molecule. Surrounding it there is also radiation continuous, all-encompassing, stretching across the entire electromagnetic spectrum, visible light from the sun above, infrared heat from the ground below, stray X-rays and gamma rays from the deep universe, along with microwave and radio waves constantly oscillating, carrying information and signals from one end of Earth to the other. Not to mention the particles that almost never reveal their presence, thousands of trillions of neutrinos silently passing through everything, and dark matter always there, yet never directly seen. So, what would happen if we stripped all of that away, if, somehow, we removed every molecule, every atom, every subatomic particle, and even each photon of radiation? Could we create absolutely nothing at all? Not just emptiness, not just a vacuum, but pure nothingness. The journey to find the answer to this question is a strange one. It takes us from simple vacuum pumps to the moment the universe was born, from ancient philosophical reflections to the fragile boundary of modern theoretical physics. Because the question, can nothingness exist or not, has a twin sibling that is no less profound. Why are we here, Dextra? The robotic arm contributed by Canada to the International Space Station is remotely controlled right on Earth, true to its name, Dextra, meaning dexterous engineers at the headquarters of the Canadian Space Agency in Quebec can operate its two multi-jointed arms via live video, helping minimize dangerous spacewalks and giving astronauts more time to rest. Sometimes, the ability to control something remotely, even from the other side of the planet, is incredibly useful. But let us return to the 17th century. In 1654, Otto von Guericke gently wiped the sweat from his forehead. Before him stood the Emperor of the Holy Roman Empire. He raised his hand as a signal. Everything was riding on this moment. A neigh rang out. Dust billowed up as two teams of horses lunged forward, pulling the rope in opposite directions. Each side had 8, equal in strength. They strained, dug their hooves into the ground, sweat dripping drop by drop. But no matter how hard they tried, they could not separate the two objects in the middle. Nothing happened. Otto smiled. Everything was unfolding exactly as planned. Otto von Guericke was the mayor of the city of Magdeburg, in the Holy Roman Empire at the time. Besides striving to restore his homeland after the brutal devastation inflicted by Catholic forces 2 decades earlier, he was also especially fascinated by new philosophical ideas. Among them, the heliocentric model that was gradually replacing the old conception of the universe. And that was precisely what led him to this famous experiment. In the ancient geocentric model, Earth lay at the center of the universe, and empty space did not exist. The universe was enclosed by crystalline celestial spheres stacked upon one another, carrying the heavenly bodies in motion without leaving any gaps. Beyond the outermost sphere, people believed was heaven. But in the heliocentric model, the planets were real physical objects, moving through a something, yet no one was sure what that something was. It could not be air, because if it were, humans would surely have felt the immense wind rushing past as Earth hurtled through space at tremendous speed. And from that moment, the question of the vacuum, of nothingness, and of whether nothing truly exists, began to become one of the deepest questions science had ever faced. So, in the end, what is the thing that the planets move through? Could it be nothing at all? Indeed, the question of whether nothingness can exist, and with it, the concept of the vacuum, has given scientists and philosophers headaches for millennia. As far back as ancient Greece, schools of thought could not reach a consensus. On one side were the atomists, led by Democritus. According to them, the entire universe is made of two basic components, atoms and void. Atoms combine with one another in countless ways, creating everything that exists from flesh, sweat, light, and air, to emotions and thoughts. And the void, or nothingness, is absolute emptiness, a foundational stage on which atoms move and from which the universe is formed. Completely opposed to that view was another line of thought, led by Aristotle himself. Like his teacher Plato, Aristotle outright rejected the concept of nothingness and the vacuum. His argument was intuitive and carried great weight at the time. A vacuum cannot be perceived by the senses. We cannot see it, smell it, or touch it. And if something cannot be experienced by any sense, then does it truly exist? Nor did it stop there. Aristotle also observed that air always tends to spread out, to fill every space and every container. Whenever humans tried to create an empty gap, air would immediately rush in to take its place. From that, he concluded, nature abhors a vacuum horror vacui. This view, spread by Aristotle with nearly absolute authority, echoed for many centuries in both the Islamic world and the West. The idea that nothingness was something that could not exist became a widely accepted truth. And then, in 1277, when the French bishop Étienne Tempier, backed by the Pope, decided to end this debate once and for all, the very concept of the vacuum came to be seen as an insult to the sacred order of the universe. His investigation arose from a theological dispute that seemed simple at the University of Paris. Could God create a vacuum or not? After all, God is omnipotent, able to do anything. But if a vacuum nothing cannot exist, then could God create the thing that cannot exist? One side argued that God's power is limitless, even surpassing logic itself. The other side countered that God created the universe along with its laws, and even he does not act against those laws. To end the dispute, Tempier issued a list of condemnations, forcing scholars to fall silent and return to orthodox boundaries. His conclusion was decisive. There is no limit to God's power. If he wished to create a vacuum, he absolutely could. Aristotle was wrong, and everything should have ended there. But university professors, silenced along one line of thought, cleverly opened up another. If God could create a vacuum, then perhaps a vacuum was allowed to exist. And if so, could humans create it themselves? About 300 years after Tempier's condemnations, an extraordinary figure laid the groundwork for answering that question. René Descartes. Today, Descartes is best known for his famous proposition, I think, therefore I am. But he also left humanity a tool that almost every modern student is familiar with, the Cartesian coordinate system. This system of perpendicular axes makes it possible to determine position, motion, and magnitude, an extremely convenient mathematical and geometrical tool. More importantly, it became a launchpad for physics, laying the foundation for Newtonian mechanics that would appear half a century later. And in a very abstract way, that coordinate system is the mathematical embodiment of empty space. If we remove all matter from the universe, the coordinate axes would still be there. Perhaps A vacuum is not impossible after all, and less than 5 years after Descartes died, the first physical evidence appeared thanks to Otto von Guericke and 16 horses. The road that led Otto to that moment was not easy. In the sacking of the city of Magdeburg 20 years earlier, he lost nearly all his property, as about 90% of the city was flattened. For decades, he struggled to free his homeland from imperial control. But alongside his political role, Otto was also a passionate scientist, and no less importantly, a brewer. It was his brewing work that made him interested in pumps used to draw water out of barrels. From there, he came up with the idea of building a mechanical system that could pump air out of a sealed chamber, the first working vacuum pump in history. This shrewd statesman quickly recognized the value of publicly demonstrating the invention. He promoted it as a symbol of Magdeburg's recovery, prosperity, and creativity. And after sending out the appropriate invitations, Otto was invited to present his experiment before Emperor Ferdinand III. He pressed 2 metal hemispheres tightly together, then used his pump to draw the air out of the empty space inside, to prove that between the 2 hemispheres there was nothing left but a vacuum. He had 2 teams of horses pull them in opposite directions. Despite their immense strength, 16 horses still could not pull the hemispheres apart. The air pressure outside was too great. It was irrefutable evidence that inside the sphere there existed something less than air, a real emptiness. Sadly, that celebrated experiment did not help Otto achieve his political goal of liberating Magdeburg, but scientifically, its consequences were profound. From that moment, the idea of the vacuum was no longer merely a philosophical or theological debate. It had become an entity that could be created, measured, and studied, opening the door to modern physics and a long journey toward answering what seemed like the simplest question of all: is nothing really nothing? A few decades after those symbolic experiments, Isaac Newton himself, one of the greatest minds in history, stepped forward to connect all the scattered pieces of human thought into a unified picture. Newton borrowed from the ancient atomists the idea that separate bodies can move freely. He took from Aristotle the observation that air always rushes in to fill empty space. He used Descartes' coordinate system, with the bold assertion that space exists as an independent entity, and he drew on Otto von Guericke's experiment, the undeniable proof that a vacuum can be created. From all of this, Newton built a complete theory of motion today called Newtonian mechanics. In this theory, an object changes its velocity only when acted on by a force. And more importantly, Newton affirmed the existence of absolute space, a stage of fixed dimensions on which all objects perform their roles. Within that space, everything moves. There is a universal force he called gravity, governing the orbits of all celestial bodies. The planets do not travel through air, but are surrounded by vacuum, a region of space where all air has been held down on the planet's surface by gravity. This is what allows them to move without friction, without drag, without slowing down. Vacuum, according to Newton, is real, and in fact, most of the universe in the Newtonian model is empty space. But Newton's genius, like every great step forward in science, opened up an even deeper question. If we can remove all matter from a region of space, leaving only pure space behind, then what carries gravity? How does light travel from the sun to the earth? How can forces act across the immense distances of nothing? Faced with that question, Newton stopped. In his writings, he frankly admitted that he could not explain that mechanism, and he left the challenge to posterity. His famous statement echoes through time: "I have not yet been able to deduce the reason for these properties of gravity from observed phenomena, and I do not feign hypotheses." Feigning hypotheses was what Newton refused to do. The answer, he believed, would come from later generations. And now we return to the original cubic meter of air. By Newton's time, both theory and experiment, accumulated over many centuries, had shown humans absolutely could create a vacuum, a box with no air, no matter. But is everything really that simple? When everything has been taken away, is anything left? There is a short story like this. Two young fish are swimming along when they meet an older fish swimming the other way. The older fish nods and says, "Morning, boys. How's the water today?" The two young fish keep swimming for a bit, and then one turns to the other and asks, "Wait, what the hell is water?" In 2005, the writer and thinker David Foster Wallace opened a commencement speech with that story. He wanted to talk about the absence of awareness that the things surrounding us, forming the foundation of our existence, are often the things we notice the least. But this story is also a perfect metaphor for an idea that dominated physics for centuries: the ether, an elusive background medium believed to fill the entire universe. To understand why this idea was born, then flourished, and finally collapsed, we have to return to the beginning of the 19th century, and begin with a shipwreck. HMS Minotaur was the pride of the British Navy. It had endured 3 major trials of war, taking part in battles against Napoleon on the Nile, at Trafalgar, and at Copenhagen. But on the night of December 22, its fate was sealed, swept into a storm off the coast of the Netherlands, separated from the fleet, in darkness under cloud cover. The ship ran aground. Not long after, Minotaur capsized and was swallowed by the sea. A total of 570 sailors died on that fateful morning. Napoleon might have taken pleasure in the enemy's misfortune, but he clearly understood the lurking danger off the coast of France to the commercial fleet, the lifeblood that sustained the war machine conquering Europe. And so, he assigned the task to a team of elite engineers and scientists to find a solution. Since ancient times, lighthouses had been used to warn sailors of hazards beneath the water and to mark coastlines. But in the modern era, with hundreds of ships crossing the oceans, the weak light of older designs was not enough. The responsibility for solving this problem was given to a young engineer, Augustin Jean Fresnel. It was a perfect choice. Before that, Fresnel had forged a breakthrough in how humans understood light. Prior to the 19th century, most scientists still believed in Newton's particle theory. That light was a stream of tiny particles, but Fresnel and his contemporaries began to see light as a kind of wave. Only with the wave theory could diffraction, the bending and interference of light, be fully explained, something the particle model could not do. With that new understanding, Fresnel set to work designing an entirely new lens system for lighthouses. In less than a century, more than 10,000 lighthouses around the world were equipped with Fresnel lenses, worthy of the title, the invention that saved 1 million ships. But Fresnel's influence did not stop at practice. He convincingly demonstrated that light is a wave, and immediately, an even deeper question appeared. If light is a wave, then a wave of what waves need: a medium to propagate. Water waves need water. Sound waves need air. So what does light vibrate in? As it crosses the emptiness between the stars. The answer began to take shape just a few decades later from a source no one expected. Many scientific revolutions begin at famous universities: Oxford, Cambridge, and countless other institutions trained minds that changed how we understand the world. But sometimes, history favors those who emerge from nothingness. Thomas Edison only attended school for a few months. Taught to read and write by his mother, Nikola Tesla never went to university. Charles Darwin studied theology at Cambridge. And then there was Michael Faraday. Unlike Fresnel with his academic background, Faraday was the son of a blacksmith. He had no formal training, learning by reading every book he could while working in a bookshop. But in return, Faraday possessed extraordinary physical intuition and a rare imagination. A century later, Albert Einstein hung Faraday's portrait beside Newton's on the wall of his office. From that humble starting point, Faraday introduced an entirely new concept into science, and through it, fundamentally changed how we understand nothingness. Faraday was part of an international scientific community that was gradually uncovering the nature of electricity and magnetism. The Frenchman Charles-Augustin de Coulomb discovered that electric charges attract and repel one another. The Italian Alessandro Volta found a way to store and discharge electricity. The American Benjamin Franklin proved that lightning and electricity are the same phenomenon. And most importantly, Faraday and his colleagues discovered a strange relationship. Electricity and magnetism are inseparable. A changing electric current creates a magnetic field, and the motion of a magnet through a coil produces an electric current. But these discoveries, just like in Newton's time, led to a haunting question. How do these forces propagate through empty space? What truly exists in what we call nothing? So how did gravity, electricity, and magnetism transmit themselves, if between two charges there is truly only an empty vacuum? How can they sense each other's electric force? It was here that Michael Faraday proposed an entirely new idea, not a force in the classical sense, not a particle, not a wave, not even quite a familiar physical phenomenon. It was a concept, the field. In Faraday's imagination, a lone electric charge is not alone at all. Around it there always exists an invisible but stable structure, the electric field. From that charge, lines of force spread out into space. And similarly, a magnet is also surrounded by a magnetic field. If you have ever sprinkled iron filings around a bar magnet, you have directly seen the shape of these lines of force. They shoot out from the North Pole, curve through space, and return to the South Pole. But for Faraday, this was not merely a visual illustration of force. He believed these lines of force were real physical entities. The mathematical expression of that idea is the field. Simply put, a field is a quantity that has a value at every point in space. When you look at a weekend weather forecast map, you are looking at a field. Each point on the map has its own temperature, pressure, or rainfall. In the case of electricity and magnetism, things are even more complicated. There is not only magnitude, but also direction. It is like a wind map of an approaching storm. Each arrow indicates both strength and the direction of motion. This idea made quite a few scientists of the time cautious, even opposed. How could something exist in the very vacuum of space? Among the early skeptics was a particularly notable name, James Clerk Maxwell, the Scottish mathematician and physicist. But Maxwell was the kind of person who could not ignore an unanswered question. It is said that since childhood, whenever he encountered something he did not understand, he would often mutter, "What is this really about?" and then emphasize it again with an even sharper question. That almost obsessive curiosity stayed with him throughout his life. It was Maxwell who took up the torch from Faraday and lifted this revolution to an entirely new level. Later, Albert Einstein hung the portraits of three men on the wall of his office: Newton, Faraday, and Maxwell. Not by accident. Maxwell realized that electricity and magnetism were not two separate phenomena. They were simply two different manifestations of a single force, electromagnetism. Depending on the situation, that force appears as an electric field or a magnetic field. He gathered the entire set of 19th century discoveries into four neat equations today, known as Maxwell's equations. And from those equations, he discovered something startling. The electromagnetic field can sustain self-propagating oscillations through space. Electromagnetic waves, when Maxwell calculated the speed at which these waves propagate, he encountered a coincidence he could not ignore. That speed was exactly the speed of light. In that moment, light revealed itself in mathematics. Light is an electromagnetic wave. Three phenomena that seemed unrelated: light, electricity, and magnetism, seen for thousands of years as completely different, turned out to be one and the same in essence. And this only became clear when Maxwell fully exploited Faraday's concept of the field. And yet, even while accepting Faraday's genius, Maxwell still hesitated on one point. He did not believe that the lines of force could exist on their own in a complete vacuum, unsupported by anything. And here, an ancient idea returned to the scientific stage. The ether. The ether has origins in antiquity, regarded as quintessence, the fifth element, the purest one, a kind of transcendent air that only gods could breathe. As astronomy and cosmology developed, many scientists tried to fill the space beyond Earth with ether, a substance lighter than air, allowing the planets to move with ease. After the discoveries of Descartes and Otto von Guericke, ether theories had weakened. Nature did not seem to hate the vacuum at all, but with light confirmed to be a wave, the ether suddenly returned, more powerfully than ever this time, as the medium that carries electromagnetic waves, and therefore carries light. The argument sounded very reasonable. Sound waves need air. Ocean waves need water. So electromagnetic waves could not propagate in absolute nothingness. If we removed everything from a region of space, surely something would remain. To test this, two American scientists set out to perform a decisive experiment. In the late 1880 seconds, Albert Michelson and Edward Morley designed an experiment later known simply as the Michelson-Morley experiment. The idea was clear, but carrying it out required near-perfect precision. They built an apparatus that could measure the speed of light in different directions. The device was arranged so that one beam of light traveled in the direction of Earth's motion around the Sun. If the ether existed, light in that direction would be pushed along, while light in the perpendicular direction would not. By this logic, over the course of a year, the measured speed of light should change, but the result did not. There was no difference at all. The speed of light was always constant. It became the most famous null result in the history of physics. There was no trace of the ether. Within just a few years after this experiment, the ether hypothesis gradually disappeared from serious science, and not long after, Albert Einstein appeared, reconciling the constancy of the speed of light, Maxwell's equations, and the absence of the ether through a radical revolution, special relativity. Einstein declared there is no absolute background for the universe, no absolute space, no absolute time. What we once called nothingness, the barren gap between objects, turned out to be a dynamic, profound, and richly structured component, more than anything we had ever imagined. So, more than half a century after Faraday reignited the issue, the picture seemed to become clear. Space truly is empty. Light, radiation, electricity, and magnetism can all propagate through vacuum without any intermediate medium. No matter, no ether, no lines of force in the classical sense, only empty space remains. Empty spaces not only exist, they make up most of the universe. And at that point, the story seemed to have closed. But of course, it never ended, because alongside Einstein's relativistic revolution, another upheaval was quietly rising: quantum mechanics. And as this new theory matured, it began to whisper then, to insist that the vacuum is not empty in the way we imagine, that nothing is. In fact, something extraordinarily complex. Before stepping fully into that strange world, let us return to our box. Now it is both emptier and more crowded than ever. We have removed all particles and radiation. We have removed the ether, the thing once thought to fill space. And yet electromagnetic fields are still there, spreading everywhere. So the question becomes, is there anything else left to remove? Or is this already the end of the journey? You have probably guessed the answer. The history of science is full of flawed estimates, sometimes by a little, sometimes fatefully. In the 15th century, astronomers and cartographers already knew the Earth was spherical. What they did not know was its exact circumference. The earliest estimate with major influence came from the 2nd century, when Ptolemy used an underestimated distance between Rhodes and Alexandria, and from that inferred Earth's circumference at about 180 stadia. More accurate measurements later showed this number was too small, and most of Europe accepted that Ptolemy was wrong. Most, but not all. Christopher Columbus believed that calculation was correct, and that crossing the Atlantic to reach Asia would take only a few months. He was wrong. And if the Americas had not been there blocking the ocean, Columbus and his crew would likely have died at sea. An error of about 25% changed human history, but that number is nothing compared to the greatest discrepancy in all of science, a gap of hundreds of trillions of times between theory and observation. And it was that discrepancy that shook the very concept of nothingness to its core. Its origin begins in the early 20th century, with an English physicist, Paul Dirac. Dirac's genius is perfectly captured in a remark by J. Robert Oppenheimer, who would later be known as the father of the atomic bomb. When writing a recommendation letter for an outstanding colleague, Oppenheimer wrote only, "He is a second Dirac, this time with human qualities." Dirac was famous for two things: frightening intellect and extreme reticence. And like Maxwell a generation earlier, Dirac did something very few physicists ever did unify. Maxwell unified electricity and magnetism, revealing the physical nature of light. Dirac went even further. He unified quantum mechanics with special relativity, and in the process, he discovered that the vacuum contains more than we ever dared to imagine. In his equations, Dirac noticed something strange: two parallel solutions. One describes the familiar world particles, like the electron. The other describes particles identical to them, but with opposite electric charge. According to those equations, interactions can produce matter and antimatter in equal amounts. In Dirac's mind, this evoked the image of an infinite ocean, a deep sea of matter, on whose surface lies all the familiar physics of our world. When you empty a box, Dirac imagined, what remains is not nothing, but that invisible ocean. The negative energy states make it normally unobservable, but sometimes, some process can pull a drop of matter out of that negative ocean and lift it into a positive energy state where we can detect it. Today, most physicists no longer view the universe exactly in Dirac's original picture of a sea of negative energy, but the core image remains, only reinterpreted in a deeper way. At very small scales, nature does not behave like anything we are used to. It does not behave like a wave, not like a particle, not like clouds, billiard balls, or a weight on a spring. In 1965, Richard Feynman opened a famous lecture on quantum mechanics with that admission, and by the 1960 seconds, Feynman and many other physicists reached a pivotal conclusion: particles are not the fundamental entities we once thought. As quantum mechanics developed, people realized that particles can appear and disappear if there is enough energy. But where do they come from and where do they go? The only answer could be the fields. In quantum field theory, the modern version of the ideas Dirac initiated, particles no longer hold the central role. Fields are the basic physical foundation. Each type of particle corresponds to its own field. The photon is tied to the electromagnetic field, the very field Faraday envisioned and Maxwell refined. The electron has its own field, the top quark, the neutrino, and every other particle type does as well. In today's standard model, there are 17 fundamental fields, and that number may still be incomplete. These fields fill all of space and time, overlapping like oil and vinegar, soaking into the same piece of dry bread. When a small region of a field oscillates, is excited to a high energy level, and begins to propagate, we observe a particle appearing, seemingly from nothingness. When that oscillation loses energy, the particle disappears. Particles can transform into one another because fields can excite each other. To our eyes, one particle vanishes and another appears, but at a deeper level. It is simply the motion and interaction of the fields. Dirac was right in his intuition. It truly is an ocean, but not an ocean of particles, an ocean of fields. And the most important thing for the question of nothing, these fields are never completely still. They are always fluctuating, relentlessly, just not at an energy level high enough for us to identify them as specific particles. In the original view, space-time was once seen as an empty stage, a blank canvas on which all the actors of the universe appear and then depart. But when space-time is combined with quantum mechanics, that picture changes completely. Wherever there is space-time, quantum fields always exist there, and therefore, nothingness is never truly an absolute vacuum. The vacuum itself carries a background energy, the lowest energy level that cannot be removed. When you take all particles and radiation out of a box, what you remove are only the strongest fluctuations. Countless other fluctuations remain microscopic tremors of quantum fields, the most basic structure of physical reality. And this is not just a tiny bit of energy hiding somewhere in the background of the universe. In theory, it is infinite. Strictly speaking, quantum fields contain an infinite number of fluctuations at every energy scale. However, in physics, what matters is not the absolute value, but the relative difference. When you drop a plate, what matters is the distance from your hand to the kitchen floor, not the height of the apartment above sea level or Earth's position in the galaxy. Similarly, every interaction between particles takes place against the backdrop of this infinite sea of fluctuations, exactly as Dirac once imagined. As long as physicists are extremely careful in how they calculate, they can still extract accurate predictions from quantum field theory. At least, that used to be the belief. But it is also possible that everything is wrong. Wrong on a scale never seen in the history of science. In the late 1992, two independent astronomy teams set out to measure a key quantity of the universe, the deceleration rate of its expansion. The universe has been expanding since the Big Bang billions of years ago, and intuitively, the gravitational pull of all matter, the total mass of stars and galaxies, should have slowed that process. If we could measure the deceleration, we could infer the total amount of matter in the universe. The Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, and the High-Z Supernova Search Team, co-led by Adam Rees, Space Telescope Science Institute, and Brian Schmidt, Australian National University, used Type Ia supernovae as standard candles to trace the expansion history of the universe. And for the first time in history, humans measured the weight of nothing. The result stunned everyone. They measured a change in the expansion rate, but in the opposite direction. The universe was not slowing down. It was accelerating. Brian Schmidt later recalled that the whole team stared at the data in a state of shock. Some were excited. Some could not believe it. Some insisted something had to be wrong. Schmidt said, "I was skeptical too, but it would be wrong not to publish a result just because we didn't like it." After months of checking, the data did not change. Finally, they sent an anxious email to the other group. "Are you seeing the same thing we are?" The answer was yes. That was the first evidence for dark energy, a mysterious entity that seems to be tearing the universe apart from within. And the simplest explanation for dark energy is precisely vacuum energy, a consequence of quantum fields. On enormous cosmic scales, these quantum fluctuations produce an anti-gravitational effect, pushing space to expand faster and faster. That means by measuring the acceleration of the universe, we can calculate the energy contained in the vacuum. The entire universe becomes a subtle measurement device for the subatomic world. And this is where the problem truly explodes. When the measured value is compared with theoretical predictions from quantum field theory, people find a discrepancy of more than 120 orders of magnitude. This is considered the largest mismatch ever encountered in science. Observations show that vacuum energy is very small, approximately the mass energy of one proton in each cubic meter of space. An almost unbelievably modest number. But the bigger problem is not that it is small, it is that it is not zero. The vacuum has energy. Fields exist. And the natural energy level of the vacuum in theory is infinite. One can imagine mechanisms that cancel the infinite part, but it is hard to understand how it could be so incredibly close to zero. And yet, not exactly zero. The vacuum carries an extremely tiny amount of energy, and we do not know why. So back to the original question, have we come closer to nothing? We have taken everything out of the box. No particles, no radiation, even Suppose we could remove the quantum fields as well, but what if we remove the box itself? If there is no longer space-time, no longer the laws that allow the box to exist, what would remain? The constants of nature, like the speed of light, or that tiny but non-zero vacuum energy, seem to be foundational to the very structure of reality. They are not merely numbers in equations. They are part of the universe itself. And there, right at the final boundary between existence and nothingness, the question still quietly echoes. Nothing in the end, does it truly exist? If you could empty a box until nothing inside it remains, there is still one thing that has not disappeared. The constants of nature are still there. They are like background rules, silently waiting outside the stage, ready to fill the box again if the right conditions are triggered. And so our mission immediately becomes far more ambitious. If the goal is to reach absolute nothingness, not only removing matter and radiation, not only removing those strange quantum fields, but going further still, is it possible to erase the very constants of nature? Nothing, in the literal sense of nothing, can it exist. It is interesting that the history of science shows sometimes the boldest questions are posed by people standing between two worlds, science and religion, two fields that seem opposed, yet have often travelled side by side. Copernicus had a doctorate in Catholic canon law and helped open the scientific revolution. Gregor Mendel was an Augustinian friar who laid the foundations of modern genetics with his pea-crossing experiments. Angelo Secchi, an Italian priest, was among the first to assert with certainty that the sun is a star. And then, there is another special figure, Georges Lemaitre. But Lemaitre did not begin as a priest. He was once a soldier in World War I. The story goes that in a Belgian army artillery notebook, there was a mathematical error in the instructions section. Lemaitre discovered it and pointed it out to his superiors. And unfortunately, people do not like being corrected. He was marked as insubordinate, and his ambitions for promotion in the army were blocked. After the war, he turned onto a different path. He entered seminary, and it was also in that journey, perhaps thanks to a background in philosophy, theology, and the patience of someone accustomed to reflecting on origins, that Lemaitre saw something very unusual hidden in equations that the world at the time was still struggling to absorb: Einstein's general relativity. In 1927, Lemaitre realized, as Einstein had realized, that general relativity naturally predicts a changing, evolving universe, not a static one. But where Einstein hesitated, even inserting a cosmological constant into the equation to keep the universe balanced and motionless, Lemaitre did the opposite. He let the equations speak for themselves, and he concluded the universe is expanding. Just 2 years later, Edwin Hubble observed the recessional velocity of galaxies and provided experimental evidence confirming Lemaitre's prediction. But what does an expanding universe mean? Lemaitre proposed an even bolder idea: the primeval atom, a state of tremendous density and energy from which the universe burst out long ago. That was the precursor of what we today call the Big Bang. However, most of his colleagues at the time mocked and dismissed this idea as too much like Genesis. The physicist Sir Arthur Eddington said bluntly, "The notion of a beginning of the present order of nature is repugnant to me." And Einstein even once spoke harshly, calling Lemaitre's physics abominable. But time has a habit of siding with evidence. Gradually, data prevailed, and in the end, Einstein not only changed his view, he became one of Lemaitre's strongest supporters. Before the Big Bang theory became the narrative framework of cosmology, the universe was like something that had always existed. It is. It was, and it forever will be. But the Big Bang, Lemaitre's primeval atom, carries an unavoidable consequence. If the universe is expanding, then it has a finite age. It has a birthday. It has an opening. But ironically, that still is not a beginning in the absolute sense. It is like the first chapter of the current book, but it does not tell us what the blank page before it was. We can calculate that about 13.8 billion years have passed since the Big Bang singularity, a finite span of time. Yet at the very moment of that singularity, our mathematics breaks. The equations blow up into irreconcilable infinities. and no known mathematical trick is powerful enough to get past them. So the question becomes naturally, terrifyingly, where did that singularity come from? And now, we return to the box. We have taken away every particle, both visible and dark. We have taken away every bit of radiation, and let us even assume we go further still. By some miracle of physics, we remove even the quantum fields from the vacuum of the box. So what is left? Is this already nothing? In the language of general relativity, the answer is no, because the box still contains something we often forget because it is always there. Like the two fish not noticing the water, it still has space-time. The stage is still there, and as long as the stage exists, the story of absolute nothingness still cannot be closed. Space-time is not merely an empty background for planets and material particles to act upon. In modern physics, it is a dynamic entity, with physical meaning as deep as any star or fundamental particle. And according to an intuition that began very early since Descartes, with his coordinate system, even if you empty a volume as much as you like, space still remains. An empty box still has length, width, height, meaning that within that emptiness there is still something, and it cannot yet be called nothing. And yet the Big Bang is considered the point of origin of the entire cosmic story, not only matter, light, or tiny particles, but space itself. If space-time has a start date at the primeval atom, the original atom in Lemaitre's picture, then the question immediately opens. Cold as a dark door before that singularity, did space exist? And if space did not yet exist, how can we even speak of before, when before requires time? At present, the answer lies outside the illuminated zone of physics that has been tested. It drifts into the realm of quantum gravity, where daring theories have tried to step forward eternal inflation. The multiverse, the Big Bounce, conformal cyclic cosmology, the no-boundary proposal. These models may try to tell a coherent story about the origin of the Big Bang, but even if they are correct, they still do not touch the deepest unease. Why is the universe the way it is now? Because there is something stranger than the question of whether space-time existed before the Big Bang. It is this: even if you imagine you could do the impossible, place a box into a state where there is no matter, no radiation, no quantum fields, not even the concepts of space and time, there still seems to be something that does not disappear. That something is physics. More specifically, there seem to be fundamental constants of nature, numbers that defy every attempt to trace their origin. They do not fall out of equations as inevitable results. They are not derived from a deeper known principle. We are forced to measure them, then plug their values into theory like nails pinning a map to the tabletop. Some constants are so familiar that we forget they are a mystery. The speed of light, for example, it is what it is. It is simply the speed at which light travels in a vacuum. We can measure it with extreme precision, but there is no way within our current understanding to predict that it must be that number. It is true that in 1865, Maxwell found the speed of electromagnetic waves and, astonishingly, it matched the speed of light. But Maxwell achieved that by combining two other constants, the vacuum permittivity and the vacuum permeability quantities that reflect how electric and magnetic forces propagate through empty space. In other words, he did not make the mystery disappear. He only showed that this mystery is tied to another mystery. Similarly, the gravitational constant is the same. Gravity has a certain strength, full stop. And deeper still lies an entire forest of constants in the subatomic world, the rest masses of particles, the binding strengths of interactions, the coupling coefficients of forces in quantum mechanics. And then, we cannot ignore the name that has loomed over modern cosmology like a massive shadow: dark energy. The vacuum has an energy level that is very small but not zero, and we have no mechanism to predict that value from first principles. What makes the picture even stranger is this: if many of those values were changed even slightly, the universe would become something entirely different, and life as we know it might not exist. Atomic structure, nuclear reactions in stars, organic chemistry, the stability of matter, all of it is far more fragile than our intuition suggests. So then, Why? Why these numbers? Exactly. Like many deep questions in cosmology. One often mentioned escape route is the multiverse. There may be countless different Big Bangs, each drawing lots to receive a set of constants and even a different set of physical laws. And we are here only because only universes like this can produce the one who asks the question. It is an idea that sounds very reasonable in a selection type way. You can only wake up in the room that has enough oxygen. But then, even that explanation carries a fatal philosophical flaw. It does not solve the problem. It only moves the marker. It may say why a constant has this value rather than that one. But it cannot answer the question, why are there constants at all in the first place? Why is there a law to draw lots? Why is there a mechanism that creates countless universes? Because that mechanism, to operate, must also follow some law, and that law then needs an explanation. The chain of whys keeps sliding onward, like an endless staircase. If string theory is right, then why exactly that many dimensions? Why strings? If eternal inflation is right, where does the inflaton field come from? And if the universe has a creator, then who created the creator? Even if you choose the most extreme hypothesis that the universe was born from nothing via some unimaginable quantum explosion, you still have to explain why quantum laws, the things that allow that explosion, exist. In 1973, the physicist Edward Tryon speculated that the entire universe might be nothing more than a subatomic quantum fluctuation amplified to cosmic scale. If the total energy of the universe is zero, balanced between the positive energy of matter and the negative gravitational energy, then perhaps the universe is just a temporary loan from quantum foam. But Tryon also could not answer the question behind it, a loan from where? And why is there a place to borrow from? And in a review of Lawrence Krauss's A Universe from Nothing, 2012, the physicist and philosophy professor David Albert hit the sore spot exactly. Particles jumping in and out of existence as quantum fields rearrange themselves is no more mysterious than a fist appearing and disappearing when your fingers close and open. Those poppings, impressive as they are, still do not move us closer to the notion of creation from nothing in the absolute sense. And so, when we speak of absolute nothingness, we are no longer speaking about what Aristotle once opposed, or what Otto von Guericke proved with 2 hemispheres and 16 horses. It is not about removing the ether that Maxwell once held onto and Michelson-Morley made disappear. It is not about taming the screaming quantum fields, first imagined by Faraday's intuition and then turned by Dirac and modern quantum field theory into a complete picture. It is not even about erasing space and time, the thing Descartes once framed with coordinates, and Lemaitre gave a birthday at the Big Bang. No, if there exists something called absolute nothing, then it must be a condition in which not only everything is taken away, but also the very thing that makes everything able to exist is taken away: the laws of physics, the constants of nature, the structure of reality, a complete silence, where even the rules that would allow that silence to be defined are gone. If one day, everything, literally everything, suddenly vanished, what would vanish even mean anymore? Imagine we return to our box. Before, we gradually emptied it, removing molecules, atoms, radiation, even reaching the edge where the vacuum still murmurs with the background energy of quantum fields. But now we go further. We do not only want to empty the box, we want to erase the very possibility of creating the box. Erase the concept of inside and outside. Erase length, width, height, erase space, erase time. Erase every law that lets us say yes or no, exist or not exist. And the question becomes unsettling because it breaks our language from within. If every foundation of reality is wiped clean, can what remains be called a condition at all? Or is even the word remains already a mistake? Perhaps it could exist, a form of absolute non-existence so extreme that even the word condition becomes meaningless, a kind of non-reality that the human mind cannot reach, because we are bound tightly to sensory experience: light, sound, Gravity, time passing, breath in and out. We can only think using things that have touched us. So if there is such a radically thorough nothingness, where even the rules for forming concepts are erased, then it lies beyond intuition, beyond description, beyond any measurement. But right here, we are pulled back to Aristotle, to the ancient argument that has haunted science for thousands of years. If something cannot be measured, cannot be observed, cannot be verified, cannot be examined, cannot even be understood, then how can we say it exists? And if we cannot say it exists, then is absolute nothingness only a self-contradictory concept, an idea that dissolves the moment we try to grasp it? Because the definition of existence demands at least one thing, the ability to be distinguished from non-existence. And so, in the debate that began more than 2,000 years ago in ancient Greece, we return to the same old question, and perhaps we will return to it forever. Can nothing exist? If the answer is yes, then reality, as we understand it, is only a special case, a fragile ripple on the surface of bottomless non-existence. If the answer is no, then even if we grind the universe down to the very end, we will always still touch something, a law, a structure, a possibility, something that prevents being from collapsing into absolute non-being. And that is where the story closes, not with an answer, but with an open door. You have just followed a journey through the biggest question humans have ever dared to ask. Why is there something instead of nothing? If you liked the way this story led you from a tiny box all the way to the edge of reality, don't forget to leave a comment telling us what you think. Thank you for watching, and see you next time.